Good morning, I'm Manuel Sarso, and in this video I'm going to talk about the concept of interaction. Okay, and I'm going to explain this with the following intuitive example. We want to study the effect of painting layer on metal type on the corrosion rate of two prototypes of metal sheets. Okay, so imagine this case. Imagine that we have metal type A and metal type B, and then we have three thickness of painting. And then imagine that we run the experiment and we obtain exactly the same value in all cases. So obviously we don't have variability. If we represent here the results, so we will see that all the values are 20, so there's no variability. The sum of squares is 0, and then so we don't have nothing to analyze. Okay, but of course in this case never happens in practice. Then let's consider this other case. So in this case, when we use the metal type A, the corrosion rate is 20. In all cases, if we use the metal type B, the corrosion rate is 30, and it's the same for any kind of the thickness of painting. So if we represent this in this plot, we will have something like this. Okay, so if we change the metal type, the corrosion rate changes, but if we change the thickness of painting, there is no change. So we will say that the total sum of squares is equal to the sum of squares of the metal, because the sum of squares of the thickness will be 0. There's no variability associated to this thickness. So the factor metal type has an effect on the mean. So when we change the metal type, there is an effect on the average value of the corrosion rate. Okay, so then let's discuss this other example. In this case, when we change the metal type, there is an effect, but also if we change the thickness, there is also another effect, because the value is not the same, it changes. So if we represent graphically the values, we have something like this. So we have in this case two lines which are parallel, and this is important. So every time that we change the metal type, there is a difference of 10 units, okay? A difference of 10 units. So we will say that the effect of the metal type is 10 units. And then when we change from 1 to 2, there is also an increase. When we change from 2 to 3, there is also an increase. But this increase, the slope of this line is the same in the two cases. It means that in this case there is no interaction, okay? And this is important. There is variability due to the effect of metal type and to the thickness. But in this case, as the lines are parallel, there is no effect of the interaction. Okay, so we will decompose the total sum of squares as sum of squares associated to metal and thickness. Then in this other example, it's more or less similar, but if we represent graphically, we can see how the slope of the lines is not the same. It means that when I am in the thickness 1, the effect of changing the metal type is 10 units. Okay, so when I change from A to B, on average, I have 10 units. But here, when I am in thickness 2, when I change from metal type A to B, the difference is 15 units, and here the difference is 20 units. So the effect of metal type depends on the level of thickness of painting. That means that there is interaction. Usually, as a rule of thumb, I say that when these lines are parallels, there is no interaction. When these lines are not parallel, there is interaction. I think that graphically it's a pretty easy way to understand the interaction. Okay. Then here we have variability due to both factors and also due to their interaction. So we will decompose and see that the total sum of squares is sum of squares of the metal thickness plus interaction. But here we have replicated the experiment twice, okay? And here we can see that every time that we replicate the experiment, we're obtaining this exactly the same value. So here we have 20, 20, 25, 25, 30, 30, and so on. Okay, so it means so because of this, there is no residual sum of squares. Okay, but this is the last case, the only one which is realistic. because when we replicate the experiment, we have a similar result but not exactly the same. So this is the only case which is realistic. In this case, the lines are not parallel, but what happens is that when I replicate the experiment, the value is not exactly the same. Okay, so the effects of the factors are partially masked or hidden by the residual variability due to uncontrolled factors. Okay, so when we carry out any kind of experimental design, there are also some kind of factors that we cannot control, and they can have some kind of effect. Okay, so this is the residual variability. So if we analyze this data with ANOVA, this is the maximum decomposition that we can achieve. Sum of squares metal plus thickness plus interaction and also plus residual. Okay, because in this case, as I was explaining, we have replicated the experiment and we are not obtaining exactly the same values. Okay, then what is the formal definition of the interaction? The interaction between two factors is when the effect of one of them is different according to the level of the factors. I think it is better to think graphically. So when the lines are parallels, we don't have interaction. When the lines are not parallels, we have interaction. But the formal definition of interaction would be this one. Okay, then this is another way to more or less visualize the interaction. So factor C, I put a minus and a plus. What does it mean? So imagine, for example, that this is temperature and we work with temperature 40 and 50. So the lowest value, the lower value is called like a minus, is represented as this minus sign, and the higher value is represented as this plus sign. And then imagine that B is another factor, it's the same. For example, it can be pressure. So when the pressure is lower, we put a minus. When the pressure is higher, we put a plus. So imagine that these are the average values that I have obtained with the four combinations of these two factors at two levels. Okay. In this case, we can see that there is an effect of factor B, because when I change from B minus to B plus, there is an increase. But when we change from C minus to C plus, there is not any kind of effect. Okay, so this is what we can say. C has no effect, B has effect, and there is no interaction because these lines are parallel. Well, this is another example. In this case, we can see how when we change to B minus to B plus, on average, there is an increase. When we change to C minus to C plus, on average, there is an increase, but the lines are parallel. It means that there is an effect of both factors, but there is no interaction. Well, this is another example where what we have is that there is an effect of factor B, because when we change from B minus to B plus, there is an increase. Also, when we change from C minus to C plus, there is an increase on average, but the lines are not exactly parallel. They are nearly parallel, but not exactly. So we will say that there is a slight interaction. This is very important because when we are going to diagnose the effect of the interaction can be a zero, so no interaction at all, or it can be slight, or it can be strong. In this example, as the lines are nearly parallel, we will say that there is a slight interaction. But this example is pretty interesting. Okay, why? Because there is no effect of factor B. So B at level minus, on average, we get this value. B at level plus, on average, we get more or less the same value. So there is no effect of B. Okay? There is no effect of B. And also C minus, on average, we get this value, and C plus, on average, we get this value. So there is no effect of C. But if we see, these lines are not parallel at all, which means that there is a strong interaction. So it can happen that there is a strong interaction, although the simple effect is not significant. And here we finish this video.